Okay, good morning. Uh, so today and tomorrow, I will try to at least finish the sections on the chapter 11 until I hope tomorrow I can get some introductions to the power series, but I think maybe not. Maybe just up until the ratio test or the root test, that is 11.7, which is actually the whole chapter. Chapter 11 is from 11.1, which is sequence, and then 11.10 or 11, that is about the Taylor series, okay, and then Maclaurin series, and the last part is I think approximation using the series. I think that is the whole content for chapter 11. It's quite long, but in the next chapter, like in chapter 12, chapter 13, it will be very short, and I think I will skip chapter 12. Okay? I will skip chapter 12, so it will not be included in your midterm. So your midterm will consist chapter 10, 11, and probably 13. Okay, probably 13. And since next week, I think I have announced in the class before. So next week there will be only TA class. Okay? So TA class on Monday, and also there will be additional TA class on the Friday. Not this Friday. This Friday is holiday, right? So the next Friday, the 6th October. Okay. So let me write here just to make sure that it's everyone know. So 2 October TA 8, 10 to 9, right? And then 6 October there will be another TA, 2-hour class. Okay. So hopefully within these hours, your TA can give you more practices about chapter 11 up until what we are going to deal with it in this week. Okay? And I also plan to give exercise that probably it will be asked in the exams, okay? Maybe from my previous exams. So I will ask TA to do that. And I don't think we need make up class because I think we are on schedule. So I think we can just start continue the course as usual for this week. Okay, so last time we have mentioned the alternating series. Okay. So the alternating series, okay, as you can see from the line number here, we start from B1. Okay? So B1 from 0, okay, B1, and then minus B2, and you will see the distance, okay, the distance B1, B2, and then B3, B4, B5, B6, it's getting decreased, and it's getting smaller. Okay? It's getting smaller. Okay? So when you plus B1, okay, it's positive, and minus B2, okay, going to the left, going to the right, left, right, left, and somehow it's reaching some points at the middle probably. Okay? So if you think that B6 going to the left, maybe you have B7 here, and then B8, B9, and then B10, and so on and so forth. So you will see that it's going to be in the middle, and it will be consistent, right? It will be consistent. It's going to be some numbers that is in between. Okay, so it's giving you a sense that we are going to have some convergence. Okay, we are going to have a convergence. We are going to have some numbers in here. So this S is actually our partial sums. Okay, if you remember, partial sums means. Let me write here. So partial sum, S1 is B1, so S2 is B1 minus B2, S3 is B1 minus B2 plus B3, S4 is B1 minus B2 plus B3 minus B4, and so on and so forth until you get this S6 and maybe S7, 8, and so forth and so on. And then from these conclusions, I think I didn't have to prove for some theory on this alternating series, but from this picture alone, we can conclude that if we have the value that is decreasing and we have alternate signs, positive, negative, positive, negative, positive, negative. The first thing, if it is decreased, okay, if the value decreased, and the second one, the limit is reaching 0. As you can see from what we have done in the system, then we can make sure that this is a convergent series. Okay? So only 2 requirements. So every time you see -1 in the front, you can check. You can check this series. You can check, take the limit. If the limit is 0 and then it's decreasing, then you can conclude it's convergent. Okay. So that's the alternating series. Okay. Remember, this limit equals 0 convergent is only we can make sure that this is only happening on the alternate series. If it doesn't have any alternate signs, if it doesn't have this -1, then we cannot use this theorem. Okay? Remember that when you get limit of the series, like any series other than alternate series, if you get limit 0, what is your conclusion? Other than alternate series, what will be the conclusion if you get limit 0? Is divergent or convergent? Other than alternate series? I think so. No. So if you get limit 0 for other series, okay. Remember, limit is neither converge or diverge, and this is not alternating. Okay? Okay, please remember this. Okay, this is very, very basic. You get wrong here, you get wrong all the concept of the series. So it's neither converge or diverge. We cannot make conclusion. Okay, if the series is not alternating, if you get limit equals 0 for this an, converge, diverge, we don't know. Okay, that's the conclusion. We don't know. If the limit has some number, maybe 1/2, what's your conclusion? No, divergent. The sequence convergent, but the series divergent. Okay, remember that. Remember that. Okay, so this is why you are getting mixed up between sequence and series. Okay? So be careful. Okay? So every time you have, so the very basic steps, you check converge or diverge, check the limit. If the limit has some number or the limit doesn't exist, you can directly write it's divergent. divergent. Okay? Remember, it's series, not sequence. If sequence is convergent, but if it is series, then we can write divergent. Okay? That's what we call the divergence test. Divergence test. Okay? So this is divergent test. Divergence test. Okay, that's alternating. And then a little bit review on the divergence test. And I hope you get this correct. Because this is the very test you can do when you have limit for the series. You take the limit, and this is the very first test you can do. You get wrong here, then wrong. All the concept wrong. Okay, so that's alternating. But in alternating, there will be some conditions, okay, some conditions that we are going to talk in the next page. And then after that, maybe we can have some examples. Okay, now there are some estimation theorem using the alternate series, okay, but I don't want to get too long on this part. So basically, the R, similar to what we have done before, the R we call the remainder. The remainder is like an error. So it's differences between some number S with the Sn. So we can think this is like our approximations using limit and the actual number. So the R is the difference between those. And of course, these differences need to be less equal to this Dn plus 1. Okay. And then for sure, number 1 and number 2 is the requirement for alternating series. And then we can have this, the remainder. But this is most likely you are going to have some approximation, make sure the error is within the range and so on and so forth. But I think we can maybe skip a little bit, okay, just to get to know what we can do in alternating series. And we can also check the error. Okay, if we have time, we can go back here to give you some more context. But I think I will just focus today on this, what we call it absolutely convergent and conditionally convergent. So, series AN is called absolutely convergent, okay, if the series of absolute values is convergent. So what does that mean? It means that every time you see alternate series, you can take the absolute values first. It means you can ignore the negative one. You can ignore the negative one in the front. And then focus on the series itself. If the series is already convergent, and of course it will make the alternate series also convergent, we call that absolutely convergent. Okay, I will give you maybe a little bit more easier way to see how we can make sure this series to be correct. Okay. So let's say we have the alternate series. Okay. We have alternate series like this, -1, n minus 1, and then 1 over n squared. Okay, what this absolute convergent means is the first thing we can ignore this -1 in front. We focus on the 1 over n squared. So we take absolute values. So if this is so an is 1 over n squared. Okay. Or let's say if we write the whole thing here, then take absolute values. Okay. And then we know that if we take the sum of the 1 over n squared, this is convergent, right? This is convergent by the, we call the P series, right? Remember we have 1 over x with power, or maybe 1 over n with power of p. When p is less than 1, or maybe less equal 1, this will be diverge. When p is greater than 1, it will be converge. So we know that this is already convergent. If we put in the alternate series, let's say we take that into some terms, okay? Let me copy this. So if you take some n, like 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus dot dot dot, you will see that it is going to be convergent. So we can say that this is convergent because the absolute value, or this one here, this 1 over n squared, is already convergent. So we can say that this is absolutely convergent. So we can say the series is absolutely convergent because the series of its absolute value is a convergent P series, and if the P is equal to, right? And then done. So every time you see alternate series, you can first take the absolute values. If it's already convergent, you can say, okay, it's absolutely convergent. For sure, it will be convergent. This -1, it doesn't really have meaning, okay, because it's already convergent. So no need to prove that it by alternate series is convergent, because by itself it's convergent. Okay. So no need to write this because we know this is convergent. Okay. So that's one way. So every time you have the alternate series, ignore the -1. Check this first. If it is convergent, we can write it's absolutely convergent. Now second, what's happened if we check this value, for example, other series, if we check the value and it's divergent, what should we do? There will be two possibilities. It can be divergent, or we can also say maybe it's conditionally convergent. So it will be converged when it is have plus minus plus minus. Okay, let me give you another context. Remember that we have the harmonic series, right? We have the harmonic series. Let me write here. Consider harmonic series. Okay, and we know that this is converge or diverge. 1 over n. Converge or diverge? Yeah, diverge. Okay, the harmonic series, right? So it's divergent. Consider harmonic series which is divergent. The harmonic series, the same series, if we put into, if it is in alternate series or alternate state, let's say it's going to be n minus 1 and then 1 over n. We are going to have 1 minus half plus 1 over 3 minus 1 over 4 plus dot dot dot. And we say that, I think already in the beginning of the alternate series, we know that this will be converged by alternate series. So since bn plus 1 is less equal bn, or maybe you can just write less equal and then limit 1 over n equals 0, the series is convergent by alternating series. Okay, now you see the difference. By itself it's divergent, but in alternate state it becomes convergent. This condition we call conditionally convergent. So it's only converged when its condition is alternate. Okay, get it? So before it's already converged, so we can just say okay, it's absolutely converged. For sure it's absolutely converged. But here, the 1 over n, only 1 over n, the series is diverged, right? But in alternate states, by the alternate series, it's converged. So it's diverged but converged in alternate series. We call the conditions conditionally convergent. Okay. So we call this. So the series. Let me write first this question. Is conditionally convergent. Okay, let me write on the more general. Let me write down here. So a series is called conditionally convergent if it is convergent but not absolutely convergent, or we can say if the series converge but the absolute value is divergent. We call this conditionally convergent. sometimes the question might ask, is it absolute convergent, conditionally convergent, or divergent? So the step by step you can try. First is take absolute value, test the series. If the series diverge, test the alternate series. If converge, then conditionally convergent. So maybe let me write the steps, okay, to help you get the logics. So first, take absolute values. Test the series. If converge, then it's absolute convergent. If diverge, you have two possibilities. Test, or maybe let me write maybe test first. Test using alternating series theorem. And then we can have if diverge or converge. If converge, then we call it conditionally convergent. Or let me write with the red color to make it clear. So take absolute values, test the series, you can use any method. If converge, then you can write absolute convergent. Test if diverge, then use alternating series. If it's still diverge, then we can say it's divergent. Or if converges, it will be conditionally convergent. Okay. So if diverge, then we can say series is divergent. Okay, any questions first? I think we can try some examples and then you can figure out how to using this diagram. So let's check the example. So determine the series, whether it's absolute convergent conditionally convergent or divergent. So number one, number two, And number 3, I'm giving you just a simple series. Okay, 3 questions. So for obvious reason, this will be defined into 3. Absolute convergent, conditionally and divergent. Okay, if the question asking between these three conditions, what is the first step? Yeah. Yeah, take absolute values. Take absolute values for all this series. And then test the series. What do you think about number 1? Take absolute values and then how to test the series. What do you think? What is the easiest test you can do?
Take the limit.
Yeah, take limit. And what's the limit? No, take limit, take limit. Right now. Take limit. You have some variable. What do you think of number 1? Yeah, you take absolute value means that we just ignore the negative number. Just do it the factor. What's the limit of this? Do you remember how to find the limit? Do you remember how to find the limit? Yeah. How? Man, you read this. Why?
No.
Why you need to read that?
No, because
Why?
to have a better understanding.
No. I'm just asking what's the limit. No need to read that.
The limit is.
No.
Why not?
No. No. Give me number 1. Yeah, divergent. Correct. Number 1 is divergent. So when you read this, you didn't get the answer.
Yes, but I'm.
Go back to your notes. Go back to your notes. And remember, this is variable 1. If you think like a polynomial, this is degree 1, right?
Yes.
This is degree 1.
Yes.
Can you divide this with n and divide this with n? Like, can you multiply with n over n? I think we can. Multiply with this.
Okay.
And then, or it means that every part here. Can we?
Yes.
Can we possibly? Can we?
Yeah.
This become?
0.
Okay, can you find? This is very, very simple calculus 1. At the early calculus 1. Okay, so check absolute value. That's this is half. So because it's 1 over 2, like I said, in divergence test, limit is not equal to, or limit is equal to value, or limit is that exists, means that the series So series is divergent. And then you can also try to check the other number as well. Let me check, what time do we have? I think we can. Yeah.
If we have some value in the alternate series is divergent.
Mm-hmm.
But if we have like 0 or the other is convergent.
You mean in the alternate series is?
If we have some value like 1 over 2, in this case is divergent.
Yeah.
But if we have 0, it will be convergent.
In alternate series.
Yes.
Yeah, in alternate series, yes. Maybe to make sure that you understand what the context is on the number 1. So we take the absolute values, it's divergent, and we take the alternate series. So because alternate series also using the limit, right? So and then check alternate series. Remember what's the requirement? First is we need to have this, and I think it's still okay. But the second one need to be need to be 0. Okay. And because the number 2 requirement is not satisfied, then we can make sure that the series is divergent. Or without taking any absolute values, just checking the alternate series, if it's divergent, and we can stop and then say, oh, it's divergent. So you don't need to take the absolute values. You can go directly here and see that, oh, it's divergent. Okay. I think the most crucial one is this last two. Because I believe from the structure itself, you can see the difference. It is greater than 1, this is less than 1. So when you take absolute values, the only one that converges is number 3. Right? This will be absolutely convergent. This will be conditionally convergent. Okay? So we can write here. So we check this is divergent because P series, P is less equal 1, right? And then the second one, what we can do is we take the alternate series and we say that that's true that Pn plus 1 is less equal Pn, which is it's decreasing, and the limit of this is equal 0. Right? So this means this is conditionally convergent. Okay. The last part is taking the absolute values, and we say this is convergent because of the P series, which is P is greater than 1. And we can just conclude that the alternate series is absolutely convergent. And maybe if you are confused on the right part here, this is requirement to be convergent. Since the limit on this series is not equal to 0, then it's not convergent. Okay, so I hope it's clear. Okay, to distinguish absolutely convergent, conditionally convergent, and divergent. Okay. You can either test the alternate series first, and then test the absolute values, and then test the series, or you can check the absolute values first and test the series. For the divergent, I think it's best to test the alternate series first. You could just like probably like at the first time you could try a trial and error at the first time, but you will see some series that is obviously okay. This should be divergent and this should be converged, but you need to prove that. Okay, I think that will be for today. Let me prepare the code first. I forgot to